I'm now going to go over a concept that's going to take what we've been learning about electric forces and apply it more generally. And that is the concept of the electric field. And this happens as a result of a single charge, or any number of charges for that matter, but it certainly starts with a single charge. And I'm going to give you a way to calculate the electric field for a single charge, but I first want you to understand what it means. If you have a charge of some size here in space, I'll just make it arbitrarily a positive charge, could be a negative charge too. If I were to put another positive charge, just if I were to, I'm not actually putting it there, just if I were to put one there, I might ask you, what would that charge experience, this charge here? I'll call it the test charge. It's not a real charge, it's an imaginary one, so to speak. It's one that I'm imagining, okay, if I could place that here, what would happen to it? And you might argue, well, it's going to be repelled by the other positive charge, so it's going to experience a force in that direction. Great. If I were to put that same test charge here, what would happen to it? You might argue the same thing. You experience a repulsive force away from the other charge. Unlike in this case, which would be to the right, in this case it would be to the upper right. In this case here, if I were to put it here, this test charge, again, you would experience a force directly away from the charge here in the center. These arrows define the direction of the electric field for each of the cases at that location. So in other words, the electric field, its direction, is defined by the direction that a test charge would experience, a positive test charge. I should emphasize that these test charges are all positive test charges. It's the direction that a positive test charge would experience a force in if it were placed at that point in space. That's the direction of the electric field. The size of the electric field, since there isn't really a charge here, there is no force you could calculate. Remember, Coulomb's law tells us this. Coulomb's law tells us that the size of the charge, the size of the force that a charge experiences as a result of being near another charge is the product of the two charges divided by the distance between the two charges squared. But if there isn't another charge here, what are we supposed to do? We can't find a force. There isn't a force to find. But what you could find is you could find the electric field, and that tells you what size force charge would experience if you knew the size of that charge. So if you knew Q2, you could find the force. But if you didn't know Q2, you'd know what force any charge of size of value Q2 would be if you placed it at the location where you're interested in finding the electric field. So in other words, I would calculate it like this. I would say, okay, the size of the electric field is equal to the K times the size of the central charge, which I'll call this one here, Q, divided by r squared, where r is the distance to your point of interest. There is not a charge there. There's just the potential to be a charge there, the ability, you could place a charge there. And if you did, you could find the strength of the force that that charge would experience simply by multiplying the electric field at that point in space times the charge that you chose to put there. That's what the size of the force would be equal to. And the direction, of course, you'd go back to this direction definition of the direction of the electric field. It's the direction that a positive test charge would experience a force in. And the size of the electric field is simply K times Q, where Q is the charge you're interested in, divided by the distance between the charge you're interested in and the point you're interested in knowing the strength of the electric field at. And as you might imagine, the units of the electric field are in units of force per Coulomb. Or, if you like, that would be newtons per coulomb. That's the definition, or sorry, the unit for electric field. So if you take the electric field and you multiply it times the charge that you're placing in that at that location where you're finding the electric field, that would give you the force that that charge would experience. That is what is meant by an electric field. And if this seems rather abstract to you, it is a little bit, because the electric field isn't something you can see, but relate it to the gravitational field. This is the Earth. The Earth has a gravitational field. You've heard that concept before, which means that if you put a mass anywhere on or above the Earth, that mass is going to experience a force that's equal to the force of gravity, which is its weight, if you want. And that weight, or that force of gravity, is simply equal to, Fg is equal to the size of the mass times g, where g is basically the gravitational field strength, which we know is 9.81 meters per second squared at the surface of the Earth. But if you go to other locations far above the Earth, g is much less. And it's always directed towards the center of the Earth, which is what these arrows represent. That is a lot like, that is the gravitational field, which is the analogy to the electric field. So you've seen this concept before in terms of gravity when you studied physics in first semester. Okay, hopefully that gives you a good introduction to the electric field.